Hello everyone and welcome to Robotics and Aerospace tutorials. In this tutorial we explain one very important topic for properly understanding kinematics and dynamics of rigid bodies. Namely, we explain the concept of rotation matrices. In particular, we will explain the meaning and derive the expression for the rotation matrix around the y-axis. In the next two tutorials, we will derive the expression for the rotation matrices around x and z axis. But before I start with explanations, I would like to mention the following. It took me a significant amount of time, energy, and planning to create this completely free video tutorial, as well as almost 400 free video tutorials that you can find on my YouTube channel. Consequently, I kindly ask you to press the like and subscribe buttons. Also, if you have a question or a comment about the material presented in this lecture, please feel free to ask your question in the comments section below. Okay, let's start. Over here, you can see two coordinate systems. The coordinate system A and the coordinate system B. The coordinate system B is rotated with respect to the coordinate system A for the angle theta around YA axis. The unit vectors of the coordinate system A are IA, JA, and KA. The unit vectors of the coordinate system B are IB, JB, and KB. We use bold letters to denote vectors. Next, observe this figure. This figure is almost the same as the previous figure except for this vector P. This vector P will play a very important role in the sequel of this video tutorial. Here's the problem that we want to solve. Knowing the coordinates of the vector P in the coordinate system B and the angle of rotation theta around the YA axis, find the coordinates of the vector P in the coordinate system A. To solve this problem, we need to introduce the following notation. The vector P with the superscript A is the vector P expressed in the coordinate system A, and with the coordinates, that is, with the projections P, XA, P, YA, and P, ZA. Similarly, the vector P with the superscript B is the vector P expressed in the coordinate system B with the projections P, XB, P, YB, and P, ZB. Over here, it should be kept in mind that the vector P expressed in A and the vector P expressed in B are actually denoting the same vector P, only expressed in different coordinate systems. The vector P expressed in the coordinate system A has this form. Over here, IA, JA, and KA are unit vectors, and PXA, PYA, and PZA are projections onto the axis XA, YA, and ZA. Similarly, the vector P expressed in the coordinate system B has this form, where IB, JB, and KB are unit vectors, and PXB, PYB, and PZB are the projections. Here, one very important thing should always be kept in mind. The unit vectors of both coordinate systems A and B are actually expressed in the same basis. That is, they are expressed by using coordinates of some other third coordinate system. Due to this, we can write this equation. P is equal to P expressed in A is equal to P expressed in B as a vector. From this equation, we obtain this equation. By substituting this equation and this equation in this equation, we obtain this equation. And this equation is very important. Next, let us scalarly multiply this equation by IA, that is, by the unit vector of the axis XA. As the result, we obtain this equation. How did we obtain this equation? Well, IA scalarly multiplying IA is equal to 1. JA scalarly multiplying IA is equal to 0. This is because JA and IA are orthogonal. KA scalarly multiplying IA is also 0. And the right-hand side is just multiplied by IA scalarly, and we obtain this equation. Next, let us scalarly multiply this equation by JA. And as the result, we obtain this equation. The logic is the same. Over here, we will only have this term due to the fact that JA is collinear with JA. They are equal, so their scalar product is equal to 1. And these other two terms, when they are multiplied by JA, will become 0. Next, let us scalarly multiply this equation by KA. As the result, we obtain the equation number 10, and the logic is the same. Next, let us group the equation 8, 9, and 10, and let us represent them together. As the result, we obtain the equation 11. This equation can be written in the matrix form. Here it is. What did I do over here? I simply took Pxb, Pyb, and Pzb, and I grouped them in this vector. And over here I took the left-hand side and I wrote the left-hand side as a vector. As the result, we obtain this matrix. Now, previously we introduced the notation, and we denoted this vector as P expressed in B. And this vector is P expressed in A. And from the equation 12, we obtain the equation 13, where the quantities, matrices, and vectors are defined over here. The matrix R, B with respect to A in this equation, is the rotation matrix. The superscript and subscript notations in R, B with respect to A mean that the rotation matrix transforms projections of a vector from the coordinate system B into the coordinate system A. This is a very important observation. Next, let us observe this figure. This figure shows the side view from the top of the unit vector of the YA axis, and it shows the unit vectors of the coordinate systems A and B. We can see the rotation over here. IA, JA, KA, as well as IB, JB, and KB are unit vectors, and consequently we have these expressions. IB scalarly multiplying IA is actually cosinus theta. We know that the scalar multiplication of two vectors is the intensity of the first one, intensity of the second one, times the cosinus of the angle between two vectors. And let us observe this figure. We have IA and we have IB, and the angle is theta. They're the unit vectors, and the result is cosinus theta. Over here, we obtain that scalar multiplication of JB and IA produces 0. This is because JB and IA are perpendicular, and consequently their scalar product is equal to 0. Let us see this term, KB scalarly IA. Let's see KB. Here is KB, and here is IA. What is the angle between these two vectors? The angle is given over here. And obviously this angle is 90 minus theta. We know that the cosinus of 90 minus theta is actually sinus theta. And taking into account that KB and IA are actual unit vectors, I simply obtain sinus theta. By using the same principle, we obtain other expressions. Next, let us substitute these expressions in the rotation matrix over here. And as the result, we obtain this matrix. This matrix is the rotation matrix defining the rotation of two coordinate systems around the y-axis. To summarize, this expression implements a mapping. It transforms the projections of the vector p expressed in the coordinate system B into the projections of the vector p expressed in the coordinate system A. Another important property of the rotation matrices is that they are orthogonal. This means the following. If I take the inverse of this matrix, the inverse will be equal simply to the matrix transposed. And you see what happened over here. I can actually switch the superscript and subscript. Why is that? Let us analyze again this equation, and let us multiply this equation by the inverse of this matrix. As the result, we obtain this equation. Now, by using the orthogonality, we obtain this equation, and finally we can say that PB is RA with respect to B, PA. That is, this matrix is the rotation matrix that transforms P in A into the P in B. And that's why we can change the superscript and subscript indices. Okay, that would be all for today. I hope that you like this video. If you like the videos I'm creating, please press the like and subscribe buttons. Thanks a lot and have a nice day.